Online. Okay. Okay. First of all, I want to thank the Department of Physics and Electronics for giving me this opportunity. Today I'll be talking about modifications to Newtonian gravity and its consequences for large-scale structures. The detailed measurements of the energy density of the universe reveal something very fascinating. The contribution from baryonic matter, that is matter that we can see, everything that you see on Earth, everything that was ever observed, made up to less than 5%, leaving the rest of the universe in the dark, with around 68% attributed to dark energy, which acts as a source of repulsive gravity, giving rise to the accelerated expansion of the universe. And the remaining 27% is attributed to matter that does not interact with light, hence dubbed dark matter. Now, the presence of dark matter has been inferred from various cosmological evidences. One major evidence being the dynamics of galaxies and galaxy clusters. It was Fritz Zwicky in 1933 who first used virial theorem to arrive at the mass of the Virgo cluster from the rotational dynamics of individual galaxies. And what he arrived at was around 400 times greater than what their luminosities could account for. Vera Rubin, along with Ken Ford, in 1970, published their findings about the rotational curves of galaxies, various galaxies, spiral galaxies. And these curves show that the velocity of stars around the outskirts of galaxies roughly move with the same velocity. Now, this is contradictory to what one would expect from conventional dynamics. From conventional dynamics, for solid disk, one would expect the velocity to increase linearly with distance. And if the mass is concentrated at the center, then velocity would decrease with the square root of the radius for distances well beyond the galactic bulge. So this is what was expected, the decrease in velocity, but what was observed was a constant velocity at distances well beyond the galactic bulge. So this basically implied that matter was increasing linearly with distances for these huge radii. So this led to the conclusion that there is a halo of dark matter around galaxies. And another best way to actually study dark matter through its interaction with visible matter. And the only way dark matter interacts with visible matter is through gravitational effects. So very direct method to do so is gravitational lensing, the deflection of photons as they pass through the warped space-time of a gravitational field. And lensing effects confirm the presence of enormous amount of dark matter both in galaxies and galaxy clusters. Now here, in this image, this image shows a cluster of a foreground cluster of galaxies that is lensing a blue background into multiple images. Here, this image shows the mass distribution. It looks like a rich galaxy of rich cluster of galaxies with the galaxy shown in these peaks. And we also see that there is a smooth component between galaxies within the cluster. And this smooth component was attributed to dark matter. Another evidence is this recent image of the bullet cluster taken by the Chandra X-ray Observatory, which shows, so basically the bullet cluster was formed after the collision of two clusters. So this image shows in pink the baryonic component and in blue the dark matter component arrived from lensing effects. Now the theory is that when the two clusters collided, dark matter smoothly passed through the point of collision without any interaction. But whereas baryonic matter slowed down due to friction and coalesced at the center of the new cluster. Another evidence is the presence of hot gas in clusters between galaxies. This image was taken by the Rosat satellite, which showed the presence of a gigantic cloud of hot gas between these two galaxies in the group NGC 2300. Now, this poses problems because to hold a very hot gas in place, we require huge amounts of very huge gravitational field. And obviously, from the visible matter, the fields that the visible matter provided was definitely not enough to hold the gas in place. So there was a huge, we require a huge component of dark matter to provide the necessary potential wealth to hold the gap in place. Now, though there are all these observations pointing out to the need for dark matter, where is dark matter, or what is dark matter? The search for dark matter has been going on for the last couple of decades, but there's no positive results so far. And also, the recent years, the sensitivity of experiments have increased in 3 to 4 orders in magnitude. Yet there is no solid evidence for their presence. And also, it's not clear what dark matter really is. There are various candidates ranging from axions with mass around 1 millionth times the mass of electron, and Wimsellas. They are named so deliberately after Godzillas because of their mass, huge masses to around trillion times the mass of a proton. There are also other candidates arising from supersymmetry and particle physics, such as gluinos, gravitinos, quark balls, Fermi balls, EW balls, etc. Also, it's not clear if dark matter is one of these candidates or is it a combination of these candidates. And if it's a combination of these candidates, then in what proportion? So all of these uncertainties around the dark matter hypothesis makes a plausible case to seriously consider alternate theories. And alternate theories work by modifying gravity, because the only way these observations are seen is through gravitational effects. One such modification is the modification of Newtonian dynamics, or MONG, which was initially proposed by Milgrom in 1983 to account for the flat rotation curves of galaxies. Now, this theory required an ad hoc introduction of a fundamental acceleration, called the MOND acceleration, of the order of 10 power minus 8 centimeter per second square. Now, when accelerations approached the MOND acceleration, the Newtonian law gets modified, giving a field strength as shown in equation 1. Here, A naught is the MOND acceleration. From this expression, we arrive at an expression for velocity as shown in equation 2. Now, this velocity, this expression is independent of radius, so thereby giving a constant velocity, accounting for the flat rotation curve. We can also arrive at these results by considering a minimum field strength or a minimum acceleration corresponding to maximum distance or maximum radius, as shown in equation 3. With this expression, here R max is the distance, is the maximum distance to which structures can grow under the influence of gravitational fields. Using the expression for R max in the usual velocity expression, we arrive at equation 6, which is again the same expression as the MOND acceleration, with A minimum replacing A naught. Thus, by doing so, by postulating a minimum acceleration, we remove the ad hoc nature of the MOND theory. Also, equation 4 constrains the sizes to which large-scale structures can grow. And with this expression, we've tabulated sizes for different clusters and galaxies, superclusters, which is shown in table 1. This is the observed sizes, and this is the limit from MOND. And we see that there is the limit from MOND is well within observed scales. Also, another explanation for flat rotation curves could come from modifications to Newtonian gravity. Now, modifications to Newtonian gravity theory is basically deal with modifications to the Poisson's equation. Here we apply modification to the Poisson's equation by considering self-energy term and dark energy term to the Poisson's expression. This is the self-energy density, and this is the dark energy term, with lambda being the cosmological constant. K is a constant of the order of g square by c square. We've also considered the density to remain constant or uniform up to a distance of around r naught from the center of the cluster, after which it the density falls down following equation 9. Now, for distances within r naught, below r naught, where the matter density dominates, it's the usual Poisson's expression giving a velocity that is linearly proportional to the distance or linearly varies with distance. But for distances well beyond R naught, the density decreases following equation 9. Thereby, the next term, the self-energy term, begins to contribute to the gravitational field. So the Poisson's equation takes the form as shown in equation 10. Here we've neglected dark energy contribution. The solution of this expression gives a logarithmic term, has a logarithmic term, as shown in equation 11, which basically implies the gravitational potential increases logarithmically. From here, we arrive at an expression for force per unit mass, as shown in equation 12. Here, k double prime is a constant, which is of the form gma minimum to the power of. Now, equating this expression for force, this is basically the expression for force per unit mass, equating this to the centripetal force per unit mass, we arrive at a relation for velocity. The r and r gets cancelled here, so you just have v square is equal to k double prime. So thereby v is equal to k double root of k double prime. That gives back the MONG velocity, gm a minimum to the power 1 by 4. A constant velocity which is independent of radius. That's accounting for the flat rotation curve. Now at larger distances very much larger than r naught. This is way beyond the galactic bulge. The densities go on decreasing and the matter density becomes so small that it is almost negligible, and we've neglected the first term. And this is when the dark energy begins to dominate. And the Poisson's expression takes the form as shown in equation 14. The solution of this expression is as shown in 15, which gives a force per unit mass as shown in equation 16. Now, expanding this, we arrive at something that looks like this. Your v prime and v are constants. And for a typical cluster, the constants are very small, of the order of 10 power minus 27 and 10 power minus 9 respectively. So for very large distances, the higher order terms of this expression can be neglected. So neglecting the higher order terms, considering only these terms, the expression for force takes this form, lambda c square r. Again, as we did earlier, equating this to the centripetal force per unit mass, we arrive at an expression for velocity that is directly proportional to radius. Again, so this thereby says that once the dark energy term begins to contribute, begins to dominate, the velocity again increases linearly with radius. So this prediction is actually more valid for galaxy clusters rather than galaxies, because the distance at which the dark energy begins to dominate is much greater than a typical size, than the size of a typical galaxy. So basically, what we've done here is we've predicted rotational velocity relation for galaxies. Now the curve has 3 regions. For typical galaxies, there are just 2 regions: the linear region and the flat region. But here there are 3 regions for clusters. There's a linear region, and then there's a flat region when the self-energy dominates. And then from the flat region, it gets back to the linear region when the dark energy begins to dominate. And this distance at which the dark energy term begins to dominate can be arrived at from the balance between the gravitational self-energy and the dark energy. This gives a relation as shown in equation 21. And for the Virgo cluster, this distance turns out to be around 14 megaparsecs. We predicted the rotational velocity versus distance relation for the Virgo cluster. Now, further observational predictions on cluster dynamics could probably support our prediction. Using MONG, we've also tried to explain infall of galaxies in the Virgo cluster by formulating an expression for the radial velocities through MONG. Now, it's well known that the velocity distance radiation in the immediate vicinity of the local group deviates from the Hubble flow because of the mass of the local group. And in this region, the gravitational field is balanced by the cosmic expansion, and the net field in this region is almost 0. So this is a region of minimum field strength, thus it comes under the MONG regime, which is subjected to accelerations as shown in equation 22, the same as the modification to Newtonian dynamics. From here, integrating this expression, we get an expression for velocity, for the radial velocity, as shown in equation 23. Here, V naught is the velocity corresponding to this region of minimum field strength. And this turns out to be same as the MOND velocity. For the worker cluster, with considering the baryonic mass of the worker cluster, this velocity turns out to be around 1,278 kilometers per second. RC here is the distance at which, or it is it's the distance at which or it's the region corresponding to minimum velocity where the field strength is minimum. And from observations, this region is found to be at a mean cluster distance of around 17 megaparsec. Using these estimates, we estimated the radial velocity versus distance relation for the worker cluster and compared this with observations. Here, the dotted line shows traces the Hubble flow with the Hubble parameter of 72 kilometers per second per megaparsec. This dark curve is our prediction from MOND. The S-shaped curve is through observations. This shows the perturbation in the Hubble flow due to the presence of the local group mass. So this work is published in these two papers. So basically here we started off by working with MOND. We removed the haddock nature of MOND by postulating a minimum acceleration. That led to the MOND results. And we accounted for the flat rotation curves of galaxies. And also we applied constraints to the sizes to which large-scale structures can grow. And we found that it is in agreement with observation. And we also looked at clusters. We extended MONG to galaxy clusters. And we predicted the velocity, the rotational velocity relation, which could be further supported through future observations. And we also predicted the infall of galaxies by considering the radial velocities, and we see it is in agreement with observation. So with this, I conclude my talk. Thank you.